If you have ever set up a freshwater aquarium, you know exactly what I'm talking about here.
Hmm.
You walk into your living room, you pull out that little master test kit.
Oh, yeah, the classic plastic box.
Right, exactly. And you fill up that little glass vial with your 5 milliliters of tank water, and you very carefully squeeze in the chemical drops.
Hoping you didn't accidentally put in 4 drops instead of 3.
Exactly, yeah.
Yeah.
And then you hold that little vial up against a white card, and you're just squinting at this color chart.
Under the kitchen light, trying to see the exact shade.
Right. Trying to figure out if the water is, I don't know, slightly blue or mostly green or somehow a color that isn't even printed on the paper at all.
Which happens a lot, yeah.
It really does.
Yeah.
And in that moment, you sort of treat that final color reading, your pH, as this ultimate pass or fail grade for your entire aquarium.
Yeah, people treat it like a report card.
Totally. Like if it's 7.0, you just breathe this massive sigh of relief. But if it's 6.0 or maybe 8.0, you completely panic.
Which is such a stressful way to enjoy the hobby.
It really is. So, welcome to the Tank Guide Life podcast. We are so glad you're joining us today.
Yeah, thanks for being here. It's a universal experience in this hobby, honestly. We see it constantly in our research on the Tank Guide.
Oh, all the time.
Yeah, like new aquarists and even veterans sometimes, they'll post these frantic messages online because their pH is, 7.4 instead of a perfect 7.0.
Right, like that 0.4 is a disaster.
Exactly. And they're ready to just dump bottles of chemicals into their tanks to fix a problem that, well, might not actually even exist.
And all because of a single number on a little paper color chart.
Yeah, it's wild.
But, our research shows that staring only at your pH is essentially like trying to understand an incoming weather system by exclusively looking at a thermometer outside your window.
That's a really good way to put it.
Right. Because sure, a thermometer tells you the temperature,
Yeah.
but it is entirely missing the wind speed, the humidity, the barometric pressure.
The massive Category 4 hurricane bearing down on your house.
Exactly. A thermometer doesn't tell you the whole story of the weather, and pH absolutely does not tell you the whole story of your water.
No, it really doesn't. And if we connect this to the bigger picture, relying on pH as like this single metric of success is exactly where so many aquarists just run into catastrophic trouble.
Mm-hmm.
It leads to this false sense of security, or on the flip side, a completely unnecessary state of panic. You just can't manage an aquatic ecosystem if you're only looking at one variable.
You really can't. So that is our mission for today. We are going to build a complete, comprehensive, beginner-friendly guide for you covering the big 3 water parameters.
The big ones, pH, GH, and KH.
Right. We're going to uncouple these 3 concepts, explain the actual biological and chemical mechanisms of what each one does in the real world.
Which is the fun part.
Oh, absolutely.
Yeah.
And we'll reveal why treating a single water parameter as though it explains your entire aquarium is just a total recipe for disaster.
Yeah, it really is.
So the overarching theme we want you to keep in the back of your mind today is this. As an aquarist, you need to target an environment, not just a single number.
Target an environment. That distinction right there changes everything about how you keep fish.
It totally shifts the mindset.
Yeah, but before we can really understand how aquarium water behaves, we have to define our terms, and we have to do it clearly.
Because the terminology is a mess.
It's a total mess. The aquarium hobby is just full of these overlapping, casually misused words that cause massive confusion.
Yeah, people throw around terms like hard water and alkaline water.
Or buffered water.
Yeah.
And they say it as if they're all synonyms, but chemically and biologically, they're incredibly different things.
So let's start with the one you're probably most familiar with, the one that causes all that anxiety, pH.
It's the famous one.
Right. We call this the right now snapshot. What exactly is a pH test measuring when you look at that color chart, like on a chemical level?
Well, at its core, pH is measuring the activity of hydrogen ions in your water.
Hydrogen ions, okay.
Yeah. Simply put, it tells us how acidic or how basic the water is right this very second.
Right this very second. That feels like an important distinction.
It's a crucial distinction. It's an intensity. It is not a capacity. It tells you absolutely nothing about what the water will do tomorrow or what it did yesterday.
It just tells you the current state of those hydrogen ions.
Exactly. It's just a snapshot in time.
Okay, let's unpack the math behind this, because I think a lot of us sort of forget high school chemistry.
Oh, for sure.
And this is where it gets really interesting and honestly, a little terrifying when you realize how the scale actually works.
The logarithmic scale.
Right. You hear that the scale goes from 0 to 14, but it's logarithmic. It's not like a ruler where every inch is the exact same distance.
No, not at all. It's heavily logarithmic.
Yep.
Specifically, a base 10 logarithm.
Base 10. Okay, so what does that actually mean for you and your fish?
Well, it means that a very, very small change in the number you see on that color chart represents a massive exponential change in the chemical reality of the water.
Okay, so let's use an example. Let's say you have a tank sitting at a pH of 7.0,
Okay.
and something happens and the pH drops to 6.0. It hasn't just gotten 1 unit more acidic, right?
No, it has 10 times the acidic hydrogen ions.
10 times from
Almost.
just a 1.0 drop.
Exactly. 10 times more acidic. And if it drops from 7.0 to 5.0, you aren't just moving 2 units down. You are dealing with 100 times more acidic hydrogen ions in the water.
Wait, really? 100 times?
Yeah. And if it drops to 4.0, that is 1,000 times more acidic than 7.0.
Wow. That tenfold arithmetic is just wild to think about.
It really puts it into perspective.
Yeah, when you realize that just a 1.0 drop in pH is a 1,000% increase in hydrogen ion activity, suddenly the hobby's deep anxiety about pH swings makes total sense.
Oh, absolutely.
You're subjecting a living creature to a completely different chemical universe.
You are. And what's fascinating here is how that math actually influences human behavior.
What do you mean?
Well, when beginners learn about that logarithmic jump, they tend to obsess over keeping the water at exactly 7.0.
Ah, right, the middle ground.
Yeah. Because 7.0 is labeled on the chart as neutral, there's this widespread assumption that it is the safest, most perfectly balanced nirvana for all aquatic life.
Yes. We see this myth everywhere in our observations.
Everywhere.
People will fight their own tap water for months, adding chemicals, just to force it down to exactly 7.0 because they think neutral pH is best for all fish.
Right.
Let's bust that right now. Why is that wrong?
Because it is a complete misunderstanding of what neutrality actually means in chemistry.
Okay, lay it on us.
Neutrality, where the pH is exactly 7 ion, is a strict chemical definition. It is the precise mathematical point where the concentration of acidic hydrogen ions perfectly equals the concentration of basic hydroxide ions in absolutely pure water.
So it's just a math equation balancing out.
Exactly. And here is the kicker, the part people forget.
Yeah.
That definition is entirely tied to temperature.
Really, temperature changes the neutral point.
Yes. It is only true at exactly 25 degrees Celsius. It's pure chemistry and thermodynamics. It has absolutely nothing to do with biological preference.
Wait, so fish don't inherently crave a pH of 7.0 just because it's biologically perfect?
Not at all. Evolution doesn't care about a human mathematical baseline.
That makes so much sense when you think about it.
Right. Just think about the habitats these animals actually evolved in over millions of years. Look at the Amazonian blackwater environments.
Oh yeah, where incredibly popular fish come from, like cardinal tetras, corydoras, discus.
Exactly. The Rio Negro doesn't sit at 7.0.
It's super acidic, right?
It is chronically heavily acidic. It often sits between a pH of 4.0 and 6.0 because of all the massive amounts of decaying organic matter, the leaves, the wood, and the sheer lack of geological minerals in the ground.
So to a discus, a pH of 7.0 is actually unusually alkaline.
Highly alkaline for them, yeah.
Yeah.
They evolved for 4.5.
And then you have the complete opposite end of the spectrum, like with the East African Rift Lake.
Oh, perfect example. Lake Tanganyika and Lake Malawi.
Right, people love those cichlids.
Yeah, and the cichlid living there thrive in chronically alkaline, mineral-rich water. Their pH regularly sits at 8.5 or even 9.0.
Wow, 9.0 is huge.
It is. So if you take a Tanganyikan cichlid and force it into your perfectly neutral 7.0 water, it will suffer.
It's like putting them on another planet.
Basically, neutrality is a mathematical property of pure water. It is not a biological preference for animals. 7.0 is not a magic ideal.
That reframes things so clearly. You really have to look at the animal's evolutionary history, not the middle of a color chart.
Exactly. You have to know where they come from.
Okay, so that is pH, the sheer intensity of the acidity right now. Let's move to the second of the big three, GH, or general hardness.
The minerals.
Right, in our research, we like to think of this as the minerals, but what is a GH test actually counting when it turns from orange to green in the tube?
So general hardness is a measure of divalent metal cations dissolved in your water column.
Okay, that sounds like deep chemistry jargon.
It is, yeah. But for practical aquarium purposes, you can think of it almost entirely as a measurement of calcium and magnesium.
Just calcium and magnesium.
Predominantly, yes. There are trace amounts of other divalent ions in there, like strontium or iron, but calcium and magnesium are the absolute dominant players.
Where do they come from?
They're abundant in the Earth's geology. Think limestone and dolomite rock. When rainwater becomes groundwater and passes through those rocks, It picks up that calcium and magnesium, dissolving it and bringing it right into your municipal tap water.
Okay, I want to clarify something right here because I see this confusion constantly.
The TDS confusion.
Yes, people buy those little digital TDS pens online. Total dissolved solids meters.
Yep, the little cheap plastic ones.
Right, and they stick them in the tank, they get a reading of, say, 300, and they say, oh, my water is super hard. So is GH just another way of saying TDS?
Emphatically no. GH and TDS are not the same thing, and confusing them can lead to serious diagnostic errors in your tank.
Okay, so break down TDS for us.
TDS stands for Total Dissolved Solids. It is a completely indiscriminate measurement.
Indiscriminate meaning it measures everything.
Absolutely everything dissolved in the water that conducts electricity. That means sodium, potassium, nitrates, sulfates, dissolved organic fish waste, liquid plant fertilizers.
And the calcium and magnesium, too.
Yes, and the calcium and magnesium that GH measures, it lumps it all together into one number.
So, if I can throw an analogy at you, tell me if this works. TDS is like weighing an entire car on a highway weigh station scale.
Okay, I like where this is going.
You are getting the total weight of the chassis, the engine, the passengers, the luggage in the trunk, and the fuel in the tank, all of it.
Yeah.
But GH, on the other hand, is just weighing the engine and the transmission.
That is an excellent way to visualize it,
Perfect.
because you can have two aquariums sitting right next to each other with the exact same TDS reading of, say, 250 parts per million.
They weigh the exact same on the scale.
Right. But Tank A might have a very high GH because that 250 TDS is made up almost entirely of essential calcium and magnesium.
A really heavy engine.
Exactly. Meanwhile, Tank B might have a GH of near zero because its 250 TDS is entirely made up of sodium, fish waste, and leftover liquid fertilizer.
No engine, just a bunch of luggage and fuel.
Yep. So if you rely on a TDS pen to tell you how hard your water is, or if you think it automatically means your water has enough minerals for your fish, you are flying completely blind.
That makes perfect sense. Okay, so why do calcium and magnesium matter so much, biologically speaking? Like, why do we care so much about the engine and the transmission of the water?
Oh, this is where we get into some truly fascinating physiology.
I know bones need calcium, obviously, but why does the water itself need it?
For freshwater fish, GH acts as a literal form of biological armor.
Biological armor, that's a strong phrase.
It really is. To understand this, you have to understand the physical reality of a freshwater fish. They are what we call hyperosmotic to their environment.
Hyperosmotic, meaning they are saltier on the inside than the water on the outside.
Exactly. They have a much higher concentration of salts and ions inside their bodies than the surrounding freshwater does.
Okay.
And because of the laws of osmosis, water constantly wants to rush into the fish's body, and their internal salts constantly want to leak out into the surrounding water.
So it's just a never-ending battle just to exist.
It really is. And their gills are the main battleground.
Because the gills are so thin and exposed to the water for breathing, right?
Right. The gills are the most vulnerable point for this osmotic leakage. Now, the epithelial cells in a fish's gills have these tiny microscopic gaps between them, which are called tight junctions.
Okay, tight junctions.
This is where the calcium comes in. The calcium that's dissolved in the water column actually physically binds to those tight junctions.
Wait, the calcium from the water binds to the fish's gills?
Yes. It acts like a chemical mortar, basically sealing the gaps between the cells. And this significantly reduces the paracellular leakage of the fish's internal ions.
That is wild. So if you have low GH, like low calcium in the water, the fish's gills literally become leakier.
Yes. In very soft, calcium-depleted water, those tight junctions weaken and open up. The mortar washes away, essentially.
Yeah.
So the fish starts losing its vital internal salts to the environment at a much faster rate. And to survive this, the fish has to kick its metabolism into overdrive.
To replace the lost salt?
Exactly. It uses a process called active transport, utilizing these specialized chloride cells in the gills to continuously pump salts back into its body against the osmotic gradient.
So it's like they are bailing water out of a sinking boat, but they have to do it 24/7 just to stay alive?
Precisely. And bailing that boat requires a massive amount of metabolic energy.
Which stresses the fish out.
Huge stress. When you provide adequate GH, you are literally saving the fish energy. You are plugging the leaks in its armor, which lowers its baseline metabolic stress.
And I assume that improves its immune function?
It improves immune function, it fights off disease, and it leaves way more energy for growth and reproduction.
That is incredible. I had absolutely no idea calcium was functioning as like an external sealant for the gills.
Yeah, it's not just about bones, it's about survival.
Okay, so we have pH telling us the acidity and GH providing the biological armor of calcium and magnesium. Let's tackle the third parameter, KH.
Carbonate hardness.
Right. But going through our research on the tank guide, it seems like the name carbonate hardness is basically a trap for beginners.
It is a terrible name. Honestly, it is responsible for so much confusion in this hobby.
Why is it called that if it's so confusing?
The term carbonate hardness is a legacy term. It was borrowed from older German water chemistry definitions. When you buy a standard aquarium KH test kit, you aren't actually measuring hardness in the way we just discussed with GH.
So it has nothing to do with the calcium and magnesium armor?
Nothing at all. You are actually measuring total alkalinity.
Total alkalinity, meaning its ability to neutralize acid.
Exactly. It measures the acid neutralizing capacity of the water. For aquarium purposes, this is predominantly made up of bicarbonate and carbonate ions.
Okay, I love the analogy we found for this, the analogy of KH as a sponge.
It's the best way to visualize it.
Imagine you have a giant sponge sitting in the middle of your tank. It's just a reservoir of neutralizing power.
A sponge is the perfect mental model
Right.
because KH is not a rigid lid that locks your pH in a fixed position.
Which is what everyone thinks it does.
It's one of the most common misunderstandings out there. People think, oh, I have high KH, therefore my pH is trapped at 8.0 and cannot move no matter what.
But that's not how it works.
Not at all. KH is a finite reservoir, a sponge, that absorbs acidic hydrogen ions as they are introduced to the water.
Okay, so let's walk through that. Let's say an acid enters the water column, maybe from fish waste or a piece of decaying plant matter.
Sure.
Instead of those hydrogen ions roaming free and just plunging the pH down, they hit the KH sponge and get absorbed.
Yes. The bicarbonate ions in the water chemically intercept the hydrogen ions, neutralizing them. And because the hydrogen ions are neutralized, they don't register on the pH test. The pH doesn't drop.
That sounds great.
It is. But here is the critical part that aquarists miss. In the process of neutralizing that acid, the bicarbonate is consumed. It is destroyed.
Oh.
Yeah, the sponge gets a little bit fuller, or rather the reservoir gets a little bit emptier.
Because a sponge can only hold so much water before it's completely saturated.
Exactly.
Oh.
The KH reservoir is finite. Once the buffering capacity is completely consumed, meaning your KH drops to 0, there is absolutely nothing left in the water to intercept the next drop of acid.
And when that next drop of acid hits,
The pH is free to crash violently downward. There's no sponge left to stop it.
this brings us to a massive myth we need to bust, which is the phrase, KH controls pH.
Ugh, people say it all the time on forums.
Just raise your KH to control your pH.
We have to correct the chemistry there.
Yeah.
KH does not dictate where your pH sits. KH determines how hard it is to move your pH.
It's the resistance.
Right. The actual resting place of your pH at any given moment is determined by a really complex equilibrium between the KH buffer reservoir and the amount of dissolved carbon dioxide and other acids currently in the tank.
So you could have high KH but low pH.
Absolutely. You can have a high KH and a surprisingly low pH if you are pumping massive amounts of CO2 into a planted tank, for example. KH is the resistance to change, not the set point itself.
Okay, this is where it gets really interesting. Because now that we know what these three parameters are in isolation, we have to look at how they interact.
Or more accurately, how they don't interact.
Right, because beginners often buy a basic pH test kit, they get a reading of 7.6, and they just assume they fully understand everything about their water chemistry.
It is a very dangerous illusion.
Why is it an illusion?
Because knowing one of these three parameters tells you absolutely nothing about the other two. They are decoupled in ways that completely shock newer aquarists when they finally get their hands on a liquid GH and KH test kit.
Okay, let's systematically dismantle one of the biggest assumptions out there. High pH means hard water.
A classic myth.
Right, people think, if my pH is 8.4, my water must be liquid rock. It must be full of calcium and magnesium.
Absolutely not. You can have water that is highly alkaline, meaning it has a high pH, like 8.4, but has a GH of absolute 0.
Wait, how is that chemically possible in the real world? Like, practically speaking.
The most common and dangerous example for hobbyists is a household water softener.
Oh, right.
Yeah, many homes in areas with naturally hard tap water install these whole house water softening units in their basement or garage.
And how do those work?
These systems use something called ion exchange resin. It is basically a big tank full of tiny plastic beads that are coated in sodium ions.
Okay, so the naturally hard water comes into the house.
The hard water, which is full of calcium and magnesium, flows over those resin beads. The resin physically strips the calcium and magnesium out of the water, trapping it.
It steals the engine?
It steals the engine, and in exchange, it releases sodium into the water. So the water flows out of your tap feeling soft, and it no longer leaves those white crusty stains on your shower doors.
But sodium doesn't register on a GH test?
Correct. Your GH is now 0. However, the original groundwater likely also had high levels of bicarbonate, which is your KH.
And the water softener doesn't touch the bicarbonate.
The water softener does not touch the KH. It leaves the bicarbonate completely intact.
Wow. So you turn on your kitchen sink, and out comes water that has high KH from the bicarbonate, which pushes the pH up to 8.4, but it has 0 GH because all the calcium was stripped out and replaced with sodium.
Exactly. Or consider regions like parts of the American Midwest. They often have natural sodium bicarbonate groundwater. The pH is sky high, the KH is sky high, but the GH is virtually 0 right out of the ground.
That is wild. Now, put yourself in the shoes of a beginner aquarist. They go to the pet store, they buy a mystery snail, they go home and test their pH. They see 8.4 on the teller chart and think, fantastic. Snails need alkaline, hard water to grow their shells. This is a perfect home for my snail.
But it's a death trap.
What actually happens to that snail in that water?
The snail's shell starts to physically erode and dissolve away into the water column. It will develop white pits, cracks, and eventually the snail will just die.
Because there is no engine. The GH is 0.
Exactly. The high pH and high KH do absolutely nothing to help that snail construct its shell. Invertebrates physically require the divalent metal cations, the calcium and magnesium that GH measures.
They need the raw materials.
Yes, they pull it directly from the water column to calcify their shells. This is why using pH as a proxy for hardness is a massive failure in diagnosis.
That is such a vivid example. Now let's push back on that and look at the inverse scenario. Can we have the exact opposite?
You mean high GH but 0 KH?
Exactly. Can I have a tank where the water is packed with minerals, high GH, but the KH sponge is completely gone, sitting at 0?
Yes, you can, and this introduces a concept called permanent hardness.
Permanent hardness.
This occurs naturally when calcium and magnesium are present in the water, but instead of being paired with carbonate or bicarbonate, which is your KH, they are paired with sulfate or chloride anions.
So like calcium sulfate?
Exactly. Calcium sulfate doesn't register as KH.
And this isn't just a geographical oddity, right? Our research shows this is an environment aquarists actually actively engineer.
Oh, absolutely.
This is exactly what high-end Caridina shrimp breeders do deliberately, isn't it?
It is a highly specialized, artificially engineered setup. Caridina shrimp, like your crystal reds or Taiwan bees, they originate from extremely soft, acidic streams.
So they need a low pH to thrive and breed.
Right. But they are still crustaceans. They still have to molt their exoskeletons, which requires, you guessed it, calcium and magnesium.
So they need the GH armor, but they need the water to be acidic. That sounds like a paradox.
It does, but breeders solve it. They start with pure reverse osmosis water. It's a completely blank slate with 0 GH, 0 KH, and 0 TDS.
Nothing in it.
Then they remineralize that water using specialized GH-only products. These products are typically based on calcium sulfate and magnesium sulfate.
So they intentionally leave the KH sponge out of the recipe.
Precisely. Because there is 0 KH-no buffering sponge to absorb acid, it allows the specialized acidic aquasoils they use to easily pull the pH of the water down into the 5.5 to 6.0 range and hold it there.
Oh, because if there was KH...
If there was KH present in the water,
yeah,
the buffer would fight the aquasoil. The aquasoil would try to release acid, the KH would absorb it, and pH wouldn't drop until the soil was completely exhausted.
So in these shrimp tanks, you have a thriving ecosystem with high GH, 0 KH, and a very low pH.
Yep, it proves how independent these variables really are.
It's just mind-blowing. Let's look at one more scenario from our observations, which perfectly encapsulates this danger for beginners. We call it the identical pH illusion.
This is a scary one.
It is. Imagine we have two aquariums sitting side by side, tank X and tank Y. You test both of them with a liquid pH test, and they both sit at exactly 7.4. To a beginner who only owns a pH kit, these tanks look like identical aquatic worlds.
But underneath that single number, they could be chemically completely different. Let's say you test the other parameters.
Right, the GH and KH.
Yeah.
Mm-hmm.
Tank Y has a GH of 16 degrees and a massive KH of 12 degrees.
So tank Y is heavily buffered. It's a fortress.
It is chemically bulletproof. You could miss a water change. You could accidentally overfeed your fish. You could have a large plant melt and rot in the corner. And that massive 12 DKH buffer sponge will easily absorb the resulting acids produced by that decay.
And the pH won't move?
The pH won't budge from 7.4. It's rock solid.
Okay, and what about tank X, the one right next to it?
Let's say tank X has a GH of 2 degrees and a KH of 1 degree.
Wow, barely anything.
Right. It still reads a pH of 7.4 today, but it is precariously soft. With only 1 DKH, the buffer sponge is the size of a postage stamp.
A postage stamp versus a giant car sponge.
Exactly. It is literally one missed water change or one dead fish away from a catastrophic chemical swing.
Because there's no capacity to absorb anything.
The moment an unexpected acid load hits that tank, it will instantly overwhelm that tiny buffer, and the pH will plummet from 7.4 down to maybe 6.0 overnight.
That is a terrifying realization for anyone who has only ever tested their pH. Identical pH readings, yet one tank's a fortress and the other is a house of cards waiting to collapse.
And you wouldn't know without the right tests.
Okay, so if identical pH readings can lie to us like that, how do we actually establish a true, honest baseline for our aquariums? If we are targeting an environment, where do we start?
You have to start at the source.
Right, the source of the water itself. For almost everyone listening, that starts right at the kitchen sink.
Tap water, well water, or arrow water. You absolutely have to know what you are starting with before you can manage an aquarium. You can't navigate if you don't know your starting coordinates.
Okay, let's talk about a phenomenon we see all the time, the tap water shift.
Oh, this causes so much panic.
Classic beginner panic. Someone writes into a forum and says, I tested my tap water straight out of the faucet and it's a perfect 7.0, but I put it in my tank and the next day I tested again and it's 7.8. I have no rocks, no crushed coral, just plain inert gravel. What in my tank is magically raising my pH?
And the answer is usually that nothing in the tank raised it. The water did it to itself.
Wait, how does water change its own pH overnight without any chemicals being added?
It comes down to dissolved gases. Municipal tap water, and especially water drawn from deep private wells, is delivered to your house under immense pressure in closed pipes underground.
Okay, high pressure.
Because it is under pressure and often draws from deep aquifers, this water is frequently supersaturated with dissolved carbon dioxide.
And what does carbon dioxide do in water?
When CO2 dissolves in water, it forms a weak acid called carbonic acid.
And acid lowers pH.
Exactly. So when you take that fresh, pressurized water straight out of the tap and immediately test it, all the dissolved CO2 and carbonic acid is artificially suppressing the pH down to 7.0.
It's pushing it down.
Right. But once you put that water into an open bucket or pour it into an aquarium where a filter is splashing and breaking the surface tension,
The water is exposed to the atmosphere.
yes, the CO2 outgasses. It physically bubbles out into the air in the room.
And as the CO2 leaves the water, the carbonic acid leaves with it.
Exactly. The acidic influence vanishes, so the pH naturally rises back up to its true equilibrium point, which might be 7.8.
So the KH didn't change?
The KH buffer didn't change at all. The mineral content, the GH, didn't change. The only thing that changed was the dissolved gas.
So what is the practical fix for this? How do people figure out their actual baseline so they don't panic?
You should always test your tap water twice.
Twice.
Okay, first, test it immediately on draw. This tells you the as-delivered pH. It's good to know this because it tells you what kind of temporary chemical shock your fish might experience if you do a massive 50 or 75% water change straight from the tap.
Right. They might get a sudden temporary hit of acidity. And the second test,
Take a cup of that same tap water, leave it sitting out on the counter uncovered for 24 hours. Or, if you are impatient, drop a bubbling air stone in it for an hour to rapidly agitate it.
to force the gas out.
Exactly.
Yeah.
Then test it again. That is your equilibrated pH. That is the true atmospheric baseline that your tank will always naturally settle toward. If you want to know what your tap water really is, that's the number you look at.
That is such a simple, practical tip that saves so much headache. Now, what about the people who have household water softeners? You mentioned them earlier with the snail shell erosion.
Right, the ion exchange systems.
Can they just use that softened water for their tanks if they add something to it?
We have to explicitly warn against using household ion exchange softened water for aquariums. It is fundamentally incompatible with most aquatic life.
Because of the sodium swap, you're removing the engine.
Exactly. You are forcibly taking out the essential calcium and magnesium that fish, plants, and invertebrates desperately need for osmoregulation and growth, and you are replacing it with sodium.
And sodium doesn't help them.
Sodium does nothing for their structural needs, and at high levels, it can actually cause osmotic stress for freshwater species.
So what do?
If you have a whole house softener, you absolutely need to bypass it for your aquarium water. Most houses have an outside spigot for garden hoses that pulls water from the main line before it hits the softening unit.
So just use the garden hose.
Use that water or get a plumber to install a dedicated bypass valve inside.
Okay, let's talk about the opposite extreme of tap water, reverse osmosis or RO water.
The blank slate.
There is a huge myth out there, especially among newer aquarists who want the quote-unquote best for their fish, that RO water is automatically better.
They think it's purified, it's pristine, it must be the healthiest thing I can give my animals.
Right, because we like to drink filtered water, so why wouldn't fish?
Well, it is incredibly pure, and that is exactly why it is deadly if it is used incorrectly.
Walk us through what RO actually is.
Reverse osmosis involves pushing water through a semi-permeable membrane at extremely high pressure. It essentially strips absolutely everything out of the water.
So it removes the bad stuff.
It removes the chlorine, the toxins, the heavy metals, the agricultural runoff, which is great, but also removes all the GH and all the KH.
It is effectively demineralized water. It's a chemical vacuum.
Pure RO water is not aquarium water. It has 0 calcium, 0 magnesium, 0 buffering capacity.
So what happens if you put a fish in it?
If you just take pure RO water and dump it into an aquarium with fish, those fish will suffer severe osmotic shock.
Because they're hyperosmotic.
Exactly. Because the water is so pure, it acts like a sponge for ions. The fish's bodies will rapidly and violently leak their internal salts outward into the pure water.
Their gills just let everything out.
Their cells will literally struggle to function. Furthermore, your aquatic plants will starve because there are no macronutrients, and your invertebrates will fail to molt and die.
So RO water isn't a finished product, it's a blank canvas.
That is the perfect way to look at it. It is a fantastic tool if your municipal tap water is unusable, like maybe it's heavily contaminated with nitrates, or it's extreme liquid rock with a GH of 25.
RO water gives you control?
It gives you total control. But as the aquarist, you must take that blank canvas and paint the minerals back in.
Remineralization.
You have to use specific remineralizing salt products to rebuild the GH and the KH to target the specific environmental needs of the fish you want to keep.
So we've got our water figured out, we've tested it, maybe we remineralized it, and we've poured it into the tank. But as we move past the setup phase, we have to acknowledge that once water is inside the aquarium, it doesn't just sit there statically.
No, it really doesn't.
An aquarium is a living, breathing, biological and chemical engine. The numbers are going to move.
And they should move. A completely static tank is a dead tank. Life generates waste, life respires, life consumes. All of that impacts the water chemistry.
Let's start with a short-term movement. The daily pH swing or the diurnal cycle.
This is a fun one.
I see people testing their water at 8 p.m. on a Monday and then 7 a.m. on a Saturday. They see 2 different numbers and they freak out, thinking their tank is crashing.
They think their tank is unstable, but what they're actually doing is capturing opposite ends of a perfectly natural, healthy breathing cycle of the ecosystem.
Walk us through the mechanism of this daily swing. Why does it happen?
It all comes back to carbon dioxide, just like the tap water shift we talked about. Let's look at the daytime cycle first.
Okay, lights are on.
During the day, if you have live plants, algae, or even just photosynthetic biofilm growing on your rocks, they're performing photosynthesis while the tank lights are on.
Which means they're growing.
Right. And to do this, they actively consume dissolved CO2 directly from the water column. As they remove that CO2, they are removing carbonic acid.
And as we know, removing acid causes the pH to rise.
Exactly. So your pH will naturally climb throughout the day, typically peaking in the late afternoon, right before the lights turn off.
Okay, so the plants are eating the acid. What happens at night when the lights go out?
At night, photosynthesis completely stops. But everything in the tank is still alive.
The fish, the bacteria.
The fish, the plants themselves, the massive colonies of beneficial bacteria, the snails, everything is respiring. They're all inhaling oxygen and exhaling carbon dioxide.
So they're breathing out CO2.
Yes. So CO2 steadily accumulates in the water all night long. That CO2 forms carbonic acid, and the pH slowly falls, bottoming out right around dawn before the lights come back on.
So a planted tank could easily read 7.4 in the morning and 7.8 in the evening, and that's not a swing they should try to fix.
Not just healthy. It is inevitable in any heavily planted tank. If you are obsessively tracking your pH to look for actual problems or crashes, you absolutely must test it at the exact same time every single day.
Otherwise, you're just measuring the breathing of the tank.
Otherwise, the data you're collecting is just diurnal noise. It means nothing.
All right, that's the daily short-term cycle. But what about the long-term trend? What drains the KH reservoir, that giant buffering sponge, over the course of weeks and months? Because if left alone, a tank's KH will eventually hit zero, right?
Yes, it will. And the primary culprit for this, and this is a mechanism that every single aquarist needs to understand deeply, is the nitrogen cycle itself.
Wait, you mean the beneficial bacteria? The
Yeah.
thing that keeps our fish from dying in their own waste is actually draining our KH buffer.
Exactly. We celebrate the nitrogen cycle, as we absolutely should, but we often ignore the chemical byproduct of it,
What's the byproduct?
the process of ammonia oxidation. That's where your beneficial bacteria consume ammonia from fish waste, convert it to nitrate, and then convert that to nitrate.
Right, the cycle.
Well, that cycle naturally produces hydrogen ions as a byproduct of the chemical reaction.
Hydrogen ions, which are pure acid,
Yes.
meaning the nitrogen cycle is essentially an acid factory.
It is a slow, relentless, invisible acid factory running 24/7 in your filter. Every single time you feed your fish, you are ultimately producing acid.
That is crazy.
Now, you don't notice this acid right away, because that acid is instantly neutralized by your KH sponge. The bicarbonate intercepts the hydrogen ions.
But remember, the sponge is finite.
Exactly. Over weeks and months, if you just top off evaporated water and neglect your actual water changes, that acid factory keeps running,
It's just chewing through the buffer.
chewing through it degree by degree. Eventually, it runs out entirely. And when it does, the acid factory keeps producing acid, but there's no sponge left.
So the pH plummets?
So it plummets, often dropping below 6.0. That is the classic textbook trajectory of what we call old tank syndrome.
So the cure for old tank syndrome, or at least the prevention, is literally just routine water changes, right?
Correct. The primary reason we do water changes isn't just to remove nitrates. It is to physically remove the accumulated acids and replenish the KH buffer with fresh tap water.
You are swapping out the saturated sponge for a fresh one.
Exactly.
We also found in our research that substrates and botanicals play a huge active role in this chemical
So
engine.
massive.
A lot of modern planted tanks use active aqua soils, those little dark brown clay pellets. How do they interact with the water?
Active aqua soils are incredibly powerful, and they are designed specifically for planted tanks and softwater shrimp. They utilize a chemical property called cation exchange.
Cation exchange, what does that mean?
The clay structure of the soil is negatively charged. It acts like a chemical magnet. It physically strips the positively charged calcium and magnesium, your GH, and the carbonates out of the water column, binding them tightly to the soil particles.
And while it does this,
While it does this, it simultaneously releases hydrogen ions acid into the water.
so these expensive bags of dirt are deliberately engineered to drop your KH to zero and push your pH down.
Deliberately and relentlessly, it creates a highly acidic, soft water environment right at the substrate level, which plant roots absolutely love because it makes nutrients highly available.
Okay, but where's the trap for beginners?
The trap beginners fall into is they buy active aqua soil, but they use hard, high KH tap water in the tank.
Oh no, so the water and the soil go to war.
Exactly. The soil tries to release acid to lower the pH. The high KH tap water acts as a massive sponge, absorbing that acid and neutralizing it.
So the soil works harder.
It rips the KH apart. You end up in this vicious cycle where the aqua soil is rapidly burning through its finite cation exchange capacity just to fight your tap water.
And then what happens to the soil?
You will exhaust an expensive bag of aqua soil in a matter of months. It renders it inert dirt instead of the 2 or 3 years it should normally last if you used it with RO water.
That's an expensive mistake. What about natural botanicals? Driftwood, Indian almond leaves, alder cones?
Oh, the tannins.
There's a massive myth in the hobby that driftwood always lowers pH. People boil a piece of driftwood for days, throw it in their citrullid tank, and expect the pH to magically drop.
This is a great nuance to highlight because it brings us right back to the KH sponge. Botanicals and wood absolutely do release weak organic acids known as tannins.
Right. These are what stain the water, that beautiful natural tea color in a black water biotope.
Exactly.
Yeah.
But color doesn't equal chemistry automatically. Tannins are very, very weak acids.
Okay, so if you have a buffer.
If your aquarium water has a high KH, say 8 degrees of KH from your tap water, that massive buffer sponge will easily absorb and neutralize those weak organic acids.
So the water turns brown, but
The water will turn dark brown. It will look exactly like the Amazon River, but the pH will not move a single tenth of a point.
So the color of the water and the pH of the water are totally decoupled.
Absolutely.
Yep.
Driftwood and botanicals only lower the pH if the KH buffer is already very low or completely depleted to zero. Only when the sponge is gone can those weak organic acids actually shift the balance of the water.
That is a massive aha moment for anyone who has been frustrated trying to naturally lower their pH.
Yeah, you can't fight a strong buffer with a weak acid.
Okay, let's touch on one more physical dynamic before we move on. Evaporation versus water changes.
Ah, the top off.
Right. A lot of beginners see the water line drop in their tank. They pour in a bucket of tap water to fill it back up, and they think they've just done their maintenance for the week.
Top-offs are emphatically not water changes.
Explain the physics there.
You have to understand the physics of evaporation. When water evaporates from your tank into the air of your living room, only pure H2O leaves. It is basically a natural distillation process.
Which means everything else stays behind.
Everything, all the minerals, the calcium, the magnesium, the nitrates, the dissolved organics, none of that evaporates. They all get left behind, concentrated in less water.
Okay, so if you top off that evaporated water using regular tap water...
You're adding new minerals from the tap water on top of the old minerals that were left behind.
Oh, I see.
Over weeks and months of doing this, the arithmetic of concentration takes over. Your GH creeps up higher and higher. Your TDS skyrockets. Your water gets harder and harder, completely altering the environment.
So how do you fix that? What is the correct way to handle evaporation?
You have to physically remove water from the tank, scoop it out, minerals and all, and replace it with fresh water. That is a water change.
And if you just need to top off...
If you are strictly doing a top-off just to replace what evaporated between water changes, you should ideally use pure RO water or distilled water. That way, you are only replacing the pure H2O that left without artificially inflating the mineral content of the tank.
Okay, this brings us to a really critical part of our discussion. Because water chemistry is so dynamic, the aquarium hobby has historically generated these universal catchphrases, these golden rules.
To stop beginners from panicking.
Exactly, to stop people from doing something stupid. Let's look at the most famous one, the one you see on every single forum post. Stable pH is more important than the correct pH.
It is arguably the single most repeated piece of advice in the entire hobby.
And is it true?
Well, while it comes from a good place, it is deeply, dangerously misunderstood.
Let's start with the good. Why does this rule exist in the first place? What behavior is it trying to stop?
The rule exists to stop aquarists from pouring bottles of raw acid or base into their tanks just to hit a magic number.
Right, chasing the 7.0.
Exactly. When you drastically alter the pH quickly, you cause rapid osmotic shifts. We talked about how fish regulate their internal salts via the gills.
The tight junctions and active transport.
Right. That process branchial acid-base compensation takes time. The fish has to physically adjust its internal chemistry at the cellular level, and that takes many hours, sometimes days.
So a fast swing is deadly.
If you swing the pH from 8.0 to 6.0 in 10 minutes, the fish cannot adapt fast enough. It suffers acute osmotic shock and can easily die. So the rule rightly teaches that stability prevents acute sudden shock. A slow transition is always safer than a fast one.
But our notes show that this rule is heavily oversimplified. Where does the rule fail? Why shouldn't we just accept a stable, wrong pH?
It fails when we ignore the concept of chronic exposure.
Chronic exposure, meaning long-term.
Yeah. Let's say you take a softwater species, like a wild-caught ram suchlid from the Orinoco Basin, and you put it in very hard alkaline tap water with a pH of 8.4 and a GH of 15.
Okay, totally wrong environment.
But the water is perfectly stable. It never changes. Will the fish drop dead today? Probably not. It survives the acute transition because it has time to adapt its osmoregulation.
But is it actually thriving?
No, it is simply surviving. Chronic exposure to the wrong chemistry has a massive cumulative cost. That ram cichlid is continuously working harder metabolically to regulate its internal ions against a massive gradient.
It's constantly bailing out the boat.
Exactly. It's under chronic stress. Over time, keeping softwater fish in hard water makes them highly prone to kidney issues.
Kidney issues? Seriously?
Yes, specifically a condition called nephrocalcinosis. Because the fish is constantly trying to excrete excess calcium it absorbs from the hard water, calcium deposits literally crystallize in the kidney tissue.
Ouch. So like kidney stones.
It's the fish equivalent of severe kidney stones, and it dramatically shortens their lifespan. Furthermore, many softwater species simply will not breed in hard water.
Because of the eggs.
Right. Their eggs require a soft, acidic environment to properly water harden and for the sperm to penetrate. In hard water, the eggs calcify too quickly and fail to fertilize.
Wow. So a stable but wrong pH might keep the fish alive so it can swim around your tank for a year or two, but you are severely compromising its health, its lifespan, and its ability to reproduce.
You're not letting it thrive.
We shouldn't just ignore the correct parameters if we want our animals to truly thrive.
Exactly. Stability is a requirement, not an excuse for poor husbandry.
But here is the scariest part of this whole discussion. We call it the ammonia grenade.
Oh, this is the big one.
This is a crucial warning for everyone listening, and it completely reframes how we think about pH stability.
This is the real hidden reason we fear sudden pH changes, and it rarely gets explained properly to beginners. The toxicity of ammonia in your aquarium is directly mathematically tied to your pH level.
Wait, really? How does that work? Let's dive deep into the chemistry of ammonia for a minute.
Okay, total ammonia nitrogen in your water exists in two distinct forms simultaneously.
Two forms.
There is ionized ammonium, which is NH4 plus I, that has a positive electrical charge and is relatively harmless to fish because it cannot easily pass through the cell membranes of their gills.
Okay, harmless ammonium.
Then there is unionized ammonia, NH3. This has no charge, is highly lipid-soluble, and easily slips directly into the fish's bloodstream.
And I'm guessing that one is bad.
Unionized ammonia is highly, highly toxic.
Okay, so you have the harmless form and the toxic form existing together. What controls the balance between them?
The pH of the water. It's driven by the concentration of hydrogen ions.
How so?
At a low acidic pH, let's say 6.0, there are tons of free hydrogen ions in the water. Those hydrogen ions latch onto the toxic ammonia and convert it into the harmless ammonium.
So at a low pH, the ammonia is safe.
At a pH of 6.0, almost 99.9% of the total ammonia exists as the harmless ammonium form.
But as the pH rises...
As the pH rises, the water becomes more basic. There are fewer free hydrogen ions available. The chemical equilibrium shifts massively.
And the hydrogen detaches.
Right. By the time you hit a pH of 8.0 or 8.5, a very significant percentage of that total ammonia is stripped of its hydrogen ion and converts back into the highly toxic unionized ammonia.
So just to be clear, a tank at 6.0 pH can hold a huge amount of total ammonia without visibly hurting the fish. But a tank at 8.0 pH with the exact same amount of total ammonia is an absolute death trap.
Precisely. And this leads us to a classic disaster scenario involving old tank syndrome, which we discussed earlier.
Walk us through it.
Imagine a tank that has been neglected for months, no water changes. The nitrogen cycle acid factory has eaten every last drop of the KH buffer sponge. The pH has plummeted to 6.0 or even lower.
And because it's so acidic, the beneficial bacteria actually stall out, right? They stop processing waste efficiently.
Right. Nitrifying bacteria don't function well in highly acidic environments.
Right.
So the cycle crashes. Total ammonia begins to build up to massive off-the-charts levels in the water. But, and this is the insidious part, because the pH is 6.0, all that accumulated waste is locked in the harmless ammonium form.
Do the fish look totally fine?
They look great. They're swimming around. Their colors are bright. They're begging for food at the glass.
And then the well-meaning aquarist finally decides to test their water.
Yep.
They see the pH is 6.0 and they panic. They remember the forum advice. They think, oh no, my pH crashed, my fish are in danger.
Exactly.
So they do a massive 80% water change with their 8.0 pH tap water, or even worse, they buy a bottle of pH up buffer and dump it directly into the tank.
And instantly, in a matter of minutes, they raise the pH of the tank from 6.0 up to 7.6.
And what happens to all that harmless ammonium?
The chemical equilibrium shifts instantly. Because the water is suddenly more basic, the extra hydrogen ions are stripped away.
The wave.
A massive, concentrated wave of harmless ammonium converts directly into lethal, toxic, unionized ammonia in a matter of seconds.
The aquarist literally pulled the pin on an ammonia grenade.
Exactly. The fish suffer severe, immediate chemical burns to their gill tissues. They gasp at the surface, their gills turn brown or bright red, and they often die within hours.
And the tragic part is?
The tragic part is that the aquarist watches this happen and thinks, oh, the pH swing killed my fish. The shock was too much. But it wasn't the osmotic shock of the pH swing. It was the sudden, violent unmasking of the hidden ammonia.
That is absolutely chilling. So what is the takeaway for the listener? How do you safely fix a tank with a crashed pH?
You must always, without exception, test for ammonia before you attempt to raise the pH or KH in an older, neglected acidic tank.
Always check for the grenade.
Right. If you test the water and ammonia is present, you cannot touch the pH yet. You have to use a chemical ammonia detoxifier like C-Sham Prime to bind the waste temporarily, and you make changes incredibly slowly.
Like small water changes.
We were talking about doing 10% water changes every few days over the course of weeks, not hours. You have to remove the physical waste before you alter the chemistry.
That leads perfectly into the second golden rule we hear constantly. Don't chase pH.
The classic.
We hear this all the time, but pet store shelves are absolutely lined with bottles labeled pH up and pH down. If they sell them, why is it such a bad idea to use them?
It all comes back to our understanding of the KH sponge. Those bottled products are fundamentally misunderstood by the people buying them.
Explain how.
Let's say you have hard tap water. Your KH is 10 degrees, and your pH sits naturally at 8.0. But you want to keep neon tetras, and you read they like a pH of 6.5.
Right.
So you buy a bottle of pH down, which is literally just a dilute acid like sulfuric acid or bisulfate, and you pour it into the tank.
I can already see the collision course here. What does the sponge do?
The buffer sponge does exactly what it is designed to do. It absorbs the acid.
So it doesn't work.
Well, when you pour the pH down in, your pH might momentarily drop to 7.0 for an hour, but over the next few hours, the massive carbonate buffer chemically neutralizes the acid you just added.
And as the acid is neutralized,
The pH bounces right back up to 8.0.
the rebound effect.
Yes. So the aquarist tests the water the next morning, sees it's back at 8.0, gets frustrated, and pours in twice as much acid.
Oh boy.
It drops, and then it rebounds again.
Yeah.
They are locked in a chemical war with their own water. They are creating a violent, artificial yo-yo effect in the tank.
Which is incredibly stressful for the fish.
This repeated, rapid swinging of the pH stresses the fish far more and is far more likely to kill them than if the aquarist had simply left them in the original stable 8.0 pH water.
So if pH in a bottle is essentially a scam for these setups, what is the right way to alter your pH if you absolutely have to for a sensitive species?
You have to alter the inputs of the environment. You don't treat the symptoms with chemical splashes.
What does altering the inputs look like?
If you need soft, acidic water, you don't pour acid into hard water. You dilute your tap water with RO water. By cutting it with RO, you physically remove half of the KH buffer sponge.
Oh, you make the sponge smaller.
Exactly. With a smaller sponge, the natural acids in the tank can gently allow the pH to fall.
And if you need to go the other way,
If you need a higher pH for African cichlids, you don't squirt pH up liquid every day. You add a bag of crushed coral or aragonite sand to your filter.
and that dissolves over time.
It dissolves slowly and continuously over months, providing a gentle, permanent, stable rise in both KH and pH. You engineer the environment. You don't just dump chemicals into it.
Engineered the environment.
Yeah.
I love that phrasing. Let's bring this all home. We've spent a lot of time talking about chemistry, buffers, ions, and gradients, but how do the animals actually experience this reality?
The physical reality of the tank.
Right. Let's talk about invertebrates, shrimp and snails. We found that they are the perfect example of why treating pH as the ultimate metric completely fails.
They absolutely are. When we talk about fish, we establish that GH, the calcium and magnesium, is primarily a metabolic factor. It plugs the gills and saves them energy.
Right.
But for invertebrates, GH is not just about saving energy. It is a hard, physical, non-negotiable structural constraint.
Because they literally wear their skeletons on the outside.
Exactly. Let's look at the molting process of a dwarf shrimp, like a neocaridina cherry shrimp. In order to grow, a shrimp has to periodically shed its old, rigid exoskeleton in a process called exesis.
Exesis.
Yeah, it breaks out of the old shell, rapidly absorbs water to expand its soft, vulnerable body, and then it has to rapidly harden a brand new exoskeleton to protect itself from predators and structural collapse.
And what is that new shell made of?
It is built primarily out of calcium carbonate, which the shrimp must draw directly from the surrounding water column. They physically extract the calcium ions from the water to calcify their new armor.
So what happens if they are living in that sodium-softened water we talked about earlier? The water has a high pH of 8.0, so the aquarist thinks it's great, but it has 0 GH, there is no calcium.
It is a horrific process for the shrimp. The shrimp attempts to molt, but there is no calcium available to build the new shell.
So it just stays soft.
It often becomes trapped inside its own half-shed molt, a condition hobbyists actually call the white ring of death, and it dies.
Mm-hmm.
Or it successfully sheds. But because it can't harden the new shell, it remains soft, lethargic, and extremely vulnerable to osmotic stress, eventually perishing.
And snails face a similar fate.
Very similar, just a slower fate.
Yeah.
A mystery snail in low GH water will literally have its shell dissolve back into the water column. The shell develops severe white pits, the tip of the spire cracks off, and eventually the snail's soft body is exposed and it dies.
They physically require the calcium and magnesium. You just can't negotiate with their biology.
Exactly, which proves why GH is so incredibly crucial.
But what about KH for invertebrates? Because we see a lot of advice out there that says higher KH is always better for shrimp and snails. Dump crushed coral in every filter. Is that actually true?
It is not always better, and it depends entirely on the species.
Hmm.
Higher KH is good for Neocaridina shrimp and most snails because they prefer harder water.
But the other
But as we discussed with the Caridina shrimp breeders, higher KH makes deliberate acidification completely impossible. If you want to breed crystal red shrimp, which require a pH of 6.0, adding crushed coral will permanently ruin your setup because the KH will lock the pH above 7.4.
And that leads to a pervasive myth about 0 kH. People constantly say 0 kH automatically equals an instant tank crash. Is that true?
It is fundamentally untrue. 0 KH removes the resistance to a crash, but it doesn't spontaneously cause one.
Explain that.
Think back to those high-end Caridina shrimp breeders. They operate massive, expensive breeding facilities at exactly 0 KH deliberately.
But how do they stop the nitrogen cycle acid factory from crashing the tank down to a pH of 4.0 and killing everything? If they have no sponge, how do they survive?
By strict, uncompromising discipline. A 0 KH tank can be perfectly beautifully stable, but it requires the aquarist to be the buffer.
The aquarist is the buffer.
Yes. They lightly stock the tanks, they feed incredibly carefully to minimize waste, they use pure remineralized RO water, and they perform routine religious water changes.
So they're controlling the inputs perfectly.
Because the bioload is so low, the amount of acid being produced by the nitrogen cycle is very small. And because their water changes are so consistent, they physically remove that acid before it can build up to dangerous levels.
So the acid production perfectly matches the mechanical replenishment.
Right. It is a precarious balance, like walking a tightrope without a net, but it is not an automatic crash. It just requires an advanced level of husbandry.
That makes total sense. Okay, before we wrap up, what about the plants? Do aquatic plants care about all this chemistry, or do they just prefer a pH?
Plants are fascinating because they interact with water chemistry on multiple levels. They don't just have a vague preference for a certain pH. They actually consume the minerals that GH measures.
Wait, plants eat calcium and magnesium?
Calcium is a crucial structural macronutrient for plant cell walls. If calcium is lacking, new leaves grow out twisted and stunted.
Wow.
And magnesium is even more critical. Magnesium is literally the central atom in the porphyrin ring of the chlorophyll molecule.
Wait, so without magnesium?
Without magnesium in the water, the plant physically cannot synthesize chlorophyll. It loses its green color, a condition called interveinal chlorosis, and it ultimately loses the ability to photosynthesize and create energy.
So extreme soft water literally starves plants of their core building blocks.
It does.
And how does pH factor into that for plants?
The pH of the water chemically dictates the availability of micronutrients in the soil and water, particularly iron.
Iron?
Iron is essential for deep green and red colors in plants. But at a high alkaline pH, iron oxidizes and becomes chemically locked up. It changes into a form that plant roots simply cannot absorb.
So a plant might be surrounded by iron fertilizer, but if the pH is 8.0, it starves to death because it can't eat it.
Exactly. This is why planted tank enthusiasts often inject CO2. Not only does it provide carbon for growth, but the resulting carbonic acid lowers the pH into the slightly acidic range, which unlocks the iron and trace minerals, making them highly bioavailable to the plants.
So when a plant cares about pH, it's really caring about how that pH affects its food supply.
Precisely. It's all connected.
This has been an absolutely mind-blowing conversation. It really changes how you look at that little glass box of water in your living room. It's not just a puddle, it's a wildly complex, interconnected chemical engine.
It really is an engine.
Let's synthesize this. If there is a main takeaway for everyone listening today, it is this. Do not treat any single water parameter as the boss.
They are a trinity, and they tell different stories.
Yeah.
pH tells us where the water is right now, the immediate intensity of the environment.
Right.
GH tells us about the essential minerals acting as biological armor for fish and structural building blocks for invertebrates and plants.
That's an engine.
And KH tells us the capacity of the water, how strongly it can resist change and absorb acids.
You have to look at the whole environment. But before we go, we wanted to leave you with one final, slightly provocative thought to mull over. We have spent this whole discussion talking about the intricacies of pH, GH, and KH. But if we really want to understand the physical stress our fish experience when we move them between different waters, from the pet store bag to our home aquarium.
We might need to look beyond pH entirely.
What do you mean?
The cutting edge of fish breeding, wild-caught acclimatization, and osmoregulatory science suggests that the hobby has been obsessed with the wrong master metric for decades. Instead of just looking at pH, we should start looking at conductivity.
Conductivity, meaning how well the water conducts electricity.
Exactly. Conductivity, measured in microsiemens, tells us the total electrical charge of all the ions dissolved in the water.
So it accounts for everything.
It accounts for everything. The GH, the KH, the sodium, the nitrates. It is the most accurate measurement of the true osmotic pressure pushing against the cells of the fish.
So moving a fish between two tanks with identical pH but wildly different conductivities
causes massive physiological stress. Understanding conductivity might be the ultimate key to unlocking breeding triggers and true biological thriving.
Conductivity, that sounds like an entirely different, incredibly deep rabbit hole for another day.
Oh, it definitely is.
Well, thank you so much for joining us on this exploration. We hope this has empowered you to look past the color chart and truly understand the water you are keeping. Remember, the next time you test your aquarium, don't just act like you're reading a thermometer. Look for the wind, feel the humidity, and understand the massive, beautiful weather system operating inside your tank. Target an environment, not just a number. This is the Tank Guide Life podcast, signing off. Keep your tanks healthy, and we will catch you next time.